This is a final presentation from Group 6, the analysis and redesign of a space heater. The portable space heater can be used to heat up a small to medium-sized room. The heater consists of a fan, motor, heating element, mounting frame, control PCB, plastic outer case, knobs, and tip-over safety switch. Customers can adjust the heat output, fan power, and the direction of airflow. If the heater is lifted off the ground or falls over, the emergency switch will automatically turn the heater off. The primary customer would be elderly homeowners, and the secondary customer would be young apartment renters. The estimated annual production is 230,000 units.
The core function of the space heater is to create your space. The first key functional requirement is to create heat. The second key functional requirement is to direct heat. You must do both of these while assuring dependability and assuring convenience.
In the function component mapping matrix, all of our components are assigned to at least one function from the FAST diagram. Components such as heating elements and the fan blades are assigned to functions related to the production and distribution of heat and air. Other components such as the control PCB and the knobs are assigned to functions related to the control of the heat and air.
Now let's look at the product family design. After comparing the FAST diagram functions with our primary and secondary customer groups, we found that only select angle and increase heat need to defer. Secondary customers, young apartment renters, have smaller spaces and don't need these features. In contrast, our primary customers, older individuals, benefit from both angle flexibility and higher heat output. We designed two variable modules to support this: the heating element, which can include an additional coil for more heat, and the stand, which can be fixed or angle adjustable. Despite these differences, the heating element frame design remains the same, accommodating either one or two heating coils. Similarly, the mounting points for the stand are standardized, regardless of whether angle adjustment is included.
In order to assess the design for manual assembly, we selected the heater element frame assembly as our platform parts and the stand assembly as our module part. Based on the quad chart, these are high functional, low manufacturing cost components. These assemblies were selected due to consisting of multiple parts, leading to high manual assembly times. For the heating element frame assembly, the 7 parts of the frame were combined into a 2-piece machined assembly that followed the following DFA guidelines: reduced part count, reduced fasteners, improved tool access, and a limited non-Z direction assembly. For the stand assembly, the stand integrated the 4 feet into its design to reduce part count. Also, a square notch was added to allow for both product variants to use the same stand design, reducing part variety. When we assessed the pre-DFA manual assembly process, the large number of parts and screws contributed to a high assembly time of 220 seconds and a low design efficiency of 17%. Changes to the heating element frame assembly and the stand assembly reduced the manual assembly time significantly. Other changes, such as adding snap-fit connections to the front and back cover and combining the fan blade and connecting it to one part, further contributed to improving the manual assembly time and assembly efficiency. These changes led to a reduced manual assembly time of 100 seconds and an assembly efficiency of 32%. Even with these drastic improvements to the assembly of the product, the reduced part count and improved manufacturing cost were achieved without compromising the primary functions of the heater.
Based on the assembly sequence, we selected the base frame subassembly for automated assembly. The original design included the back cover, heating element frame, 6 fork brackets, and 4 fasteners. The new design after DFA is the back cover, 2 slightly different heating element frame parts, and only 2 fasteners. The respective explosive fuse are shown on the left. We eliminated all 6 brackets and simplified the frame design into 2 simple parts. Our automation decision makes sense when referencing the quad chart shown on the right. The high manufacturing cost and high important parts were not chosen because they are electrical components. The feet were eliminated from the design. The 3 parts chosen were from the high functional but low manufacturing cost section highlighted in yellow. The 2 tables on the slide show both our pre-DFA and post-DFA automated assembly and insertion costs for each item in the subassembly based on our annual production volume of 230,000 units, resulting in a cycle time of 2.4 units per minute. Our pre-DFA total cost was 30.83, and our post-DFA total cost is now 6.68. 3 DFA principles used in our redesign are: DFA 1, the reduction of parts with the elimination of the 6 port brackets by incorporating their function into the heat element frame parts; DFA 2, reduction in fasteners. We reduced the initial 4 screws that attach the frame to the back cover down to 2. DFA 4, allowing hand and tool access better to the screw locations. Subsequent fan assembly with a much less restrictive heat element frame design. There are no impacts to the product function from this redesign. Overall manufacturing costs will be reduced due to the reduction in parts complexity and improved assembly.
The part redesign was a heater frame, where previously was an assembly of the frame and the support brackets. The material we chose for our heater frame was the aluminum alloy. Since the frame will only hold a heating element, we decided to determine both tolerances and the surface roughness as non-critical. We evaluated several manufacturing processes, and out of all of the machining and sheet working stood out the most suitable options. But because of the shape of the material, we decided to go with the machining as it meets our performance and dimensional requirements.
The stand part of the heater assembly was modified with 2mm fillets to allow the 4 outer slots to be all cut without having to remount the workpiece during milling. It was then analyzed by the DfM Pro software, which only found 2 sharp edges that could be modified to better meet the best practices of DFMC-15. The stand part has an estimated cost per part of $2.83, which was negligibly increased due to applying DfM best practices. The post-DFA mount uses 2 of the same mounting through holes as the original assembly. The mount part of the heater assembly was also modified with 2mm fillets to allow for the 4 outer slots to all be cut without having to remount the workpiece during milling. It was also analyzed by the DfM Pro software, which found no further issues or recommendations. The mount has an estimated cost per part of $3, which was negligibly decreased after having the DfM best practices applied. When looking from the analytical method, the changes in the cost per part due to applying DfM to the assembly seems to cancel out at an estimated cost per part of $5.83. Both pre- and post-DfM parts were quoted online to compare with the analytical cost calculations. The key takeaway from the hub's estimates increased cost of post-DfM parts is that there is further room for optimization, like custom extruded starting material, that is not fully covered by our analytical cost calculations. In addition, the cost increase for post-DfM parts may be able to be explained as error in the extrapolation, as the max value of units from the hub's website allows for was 200, which is a few orders of magnitude smaller than the estimated units of 230,000 for each part.
The part redesign was the fan blades, where our initial design was an assembly between fan blades and the fan connector. The material we chose was nylon, a thermoplastic with a solid 3D geometry. Based on our requirements, we evaluated several processes for thermoplastics, where only the process that stood out, meeting all our requirements, was injection molding.
The estimated cost was around 48 cents to injection mold the pre-DfM fan blades. The maximum wall thickness causes high operating costs. With DfM Pro, the team was able to modify the design according to its suggestions. 5-degree draft angle was added and the blade's wall thickness was uniform to 2 mm. The center connector part, where the maximum wall thickness is reduced from 4.6 to 2.5 mm. Sharp corners were also modified during the process. After DfM, the estimate cost was reduced to 33 cents per part. Although the material cost is higher due to wall thickness uniformation, the operating cost was significantly reduced. Without impacting the assembling process, the redesign increases functionality in terms of strength and durability. The applied DfM guidance are DFIM 1, 2, 3, and 4.
Enhancing the product family after design for manufacturing, a smart control can be integrated to form a product service system. This service includes a remote control feature, both physical and app-based, that allows the user to adjust heat level, fan speed, set timers, and enable or disable the auto shut-off capability. This system will be able to connect via Bluetooth or sync on a home Wi-Fi. There's many features that include remote control feature, energy saving feature, energy tracking to show estimated usage recommendations, optional integration with smart home assistants, and service reminders. Firmware updates will enable us to extend the product life and add future features.
Overall, our group drastically improved the original design of the heater assembly. The manual assembly time was reduced by 2 minutes, and the automated assembly cost per part was improved by $16. While there was minimal improvement for the heating element frame cost during the design for manufacturing, the fan blade cost was reduced by 15 cents per part. The pros of our changes involved the significant part and screw count reduction and the improved part complexity for variants, while our biggest con was adding new rods into the product to facilitate and improve rotation of the heater. If we were to start this project again, we would select an initial heater that had a higher part count to allow for further part consolidation. Overall, our group drastically improved the original design of the heater assembly. Thank you.